how do we select models and how do we evaluate them? The fundamental tension in ML is between bias and variance, which we call bias-variance trade-off. The bias is the error due to the oversimplification of the model, which can lead to underfitting, as a poor performance in both training and test data. And variance, which is the error due to excessive complexity of the model, which can lead to overfitting, which is good performance in training data but poor generalization to new data. A technique used for estimating a model's performance in unseen data is cross-validation, where we split the data set into multiple folds, and the model is trained and evaluated on different combinations of folds, providing more robust estimate of its generalization ability. Some performance metrics: accuracy, which is a proportion of correct predictions; precision, which is a proportion of true positive predictions among all positive predictions; recall, also known as sensitivity, which is a proportion of true positive predictions among all actual positive instances; the F1 score, which is a harmonic mean of precision and recall, providing a balanced measure for imbalanced data sets; the mean square error, or the MSE, which is a common metric for regression tests, measuring the average squared difference between predicted and actual values. Overfitting is when the model learns the training data too well, capturing noise and random fluctuations instead of the underlying patterns. This can lead to poor generalization of new data. Some signs of overfitting are high training accuracy but low test accuracy, overly complex decision boundaries. Some ways to mitigate overfitting: regularization, where we add a penalty term to the loss function to discourage complex models, for example L1 or L2 regularization; early stopping, or halting training before the model starts overfitting, or using more training data, which is often the most effective way to reduce overfitting. Underfitting is when the model becomes too simple to capture the underlying pattern in the data, resulting in poor performance on both training and test data. Some signs are low training and test accuracy, inability to capture complex relationships in the data. Some ways to mitigate this: use a more complex model, add more features, increase model capacity by adding more layers in the neural network, or feature engineer and create more informative features that better represent the underlying pattern. Some ethical considerations: bias in data. ML models can inherent biases present in the training data, leading to discriminatory outcomes. It's crucial to carefully curate and pre-process data to ensure fairness and avoid perpetuating harmful biases. Fairness. ML systems should be designed to treat all individuals or groups equitably, regardless of sensitive attributes like race, gender, or socioeconomic status. Transparency. ML models should be explainable, meaning the decision-making process should be understandable to humans. This is important for building trust and ensuring accountability. Developers and deployers of ML systems should be held responsible for the ethical implications and potential negative consequences. Let's now discuss some key machine learning algorithms. A key category of machine learning algorithms is linear models, where we model the relationship between a continuous dependent variable, the targets, and one or more independent variables, features, using a linear equation. The goal is to find the best fitting line, or hyperplane in higher dimensions, that minimizes the sum of squared errors between the predicted and actual values. The classic equation for linear regression is y equals to beta O plus beta 1 x1 plus beta 2 x2 plus epsilon, where y is the predicted value, bn is the intercept, bo is the intercept, b1 and bn, b2, bn are the coefficients or the weights of the features x1, x2, xn, and e is the error term. Some applications of linear regression are predicting house prices based on square footage, number of bedrooms, etc. Forecasting sales based on advertising spending, seasonality, etc. Estimating crop yields based on rainfall, temperature, etc. Strengths of this is extremely simple to use, it's highly interpretable, and computationally efficient. Some weaknesses are it assumes a linear relationship and it's sensitive to outliers, which makes it a non-ideal option for most real-world applications. Logistic regression, where we use a classification algorithm that extends linear regression for binary classification problems. That is yes or no, true or false. This models the probability that an instant belongs to a particular class using the logistic function or the sigmoid function. The equation for this is the probability that y equals 1 given x is equal to 1 divided by the quantity 1 plus e raised to the negative of the linear combination of beta 0 plus beta 1 times x 1 plus beta 2 times x2 and so on up to beta n times. Some applications of this are email spam detection, predicting customer churn, and medical diagnosis, for example, the presence and absence of diseases. Strengths of this are it provides probabilities for class membership, it's interpretable, handles binary and multi-class classification. Some weaknesses are it assumes a linear relationship between features and log odds and will not perform well with complex decision boundaries. Support vector machines. This is a powerful algorithm for both classification and regression tasks. SVMs find an optimal hyperplane that maximally separates different classes in classification of its data in regression, while maximizing the margin, which is the distance between the hyperplane and the nearest data points. The key concepts are support vectors, which are the data points that lie closest to the decision boundary and influence its position the most. Kernel trick, a technique that allows SVMs to implicitly map data into higher dimensional spaces where linear separation might be possible even if it is not in the original space. Applications of this are image classification, text categorization, bioinformatic analysis, for example, protein classification. Strengths, effective in high dimensional spaces, versatile with different kernel functions, and robust to outliers. Weaknesses, can be computationally expensive, less interpretable with complex kernels. Let's talk about tree-based models now. Decision trees, which is a hierarchical model that recursively partitions the data space based on feature values. Each internal node represents a test on a feature, each branch represents an outcome of the test, and each leaf node represents a class label or a numerical prediction. Building a decision tree. Start at the root node, consider all features, and choose the one that best splits the data based on the criterion. For example, Gini impurity for classification and mean squared error for regression. Split the data into subsets based on the chosen feature's value, and recursively apply steps 1 and 2 to each subset until a stopping criterion is met, for example, maximum tree depth reached or minimum number of samples per leaf. Some examples are predicting whether a customer will churn based on features like age, income, contract length, etc. The tree might split on age first, then income, and so on, leading to different churn probabilities in the leaf nodes. Strengths, interpretable, easy to visualize and understand the decision-making process, handles both categorical and numerical data, no need for feature scaling. Non-linear relationships can capture complex interactions between features. Weaknesses, prone to overfitting, can memorize the training data if not pruned or regularized. Instability, Small changes in the data can lead to very different trees. Greedy approach may not find the globally optimal tree. Random forest, which is an ensemble learning method that combines multiple decision trees to improve prediction accuracy and reduce overfitting. Each tree is trained in a random subset of the data, which is called the bootstrap sampling, and a random subset of features. Bagging. The process of creating diverse trees by training each one a different bootstrap sample of the data. This reduces the variance of individual trees and makes the overall model more robust. Random feature subsets. At each node, a random subset of features is considered for splitting, further increasing diversity among trees and reducing correlation. Prediction. The predictions of all trees are averaged for regression, or a majority vote is taken for classification. Strengths of random trees. Random forests. Provides excellent performance, often outperforms individual decision trees and many other algorithms. It's robust to overfitting. The ensemble approach reduces variance and improves generalization. Handles high-dimensional data. Can select important features automatically. Weaknesses. Less interpretable. The decision process is less transparent than a single decision tree. Computational costs. Training many trees can be computationally expensive. Let's talk about gradient boosting machines, or GBMs, which are another ensemble learning method that combine multiple dimensional decision trees but in a sequential manner. Each tree is trained to correct the errors in the previous trees. The algorithm focuses on instances that were misclassified, had large residuals in previous iterations. Boosting. There's a process of combining weak learners, that is, the models that are slightly better than random guessing, into strong learners. GVMs use decision trees as weak learners. Gradient descent, which is an algorithm used to minimize the loss function that measures the errors of the ensemble. The gradient of the loss function guides the training of each new tree. Strength. High predictive power. Often achieves state-of-the-art performance in various tasks. Handles mixed data types. Can deal with both numerical and categorical features. Feature importance. Provides insights into which features are most important for prediction. Weaknesses. It's prone to overfitting if not tuned correctly. Requires careful control of parameters like learning rate, tree depth, and number of trees. The computational costs can be slow to train, especially with large data sets and complex models. Neural networks and deep learning. The fundamental building block of the nervous system is the biological neuron, which is what inspires the artificial neural network. The neuron receives signals or inputs from other neurons through dendrites, processes the signals in the cell body, and transmits the output signal through the axon. A simplified model of this is the artificial neuron, which is also called a perceptron, which receives multiple inputs, each multiplied by a weight, sums them up, applies an activation function, and produces an output. The activation function introduces non-linearity into the model, allowing it to learn more complex relationships between inputs and outputs. Common activation functions include sigmoid, rectified linear units, and hyperbolic tan functions. Feed-forward neural network, FFNN. The structure of this is composed of multiple layers of interconnected artificial neurons. But the input layer receives the raw input features, the hidden layer processes the input data through multiple layers of neurons, learning increasingly complex representations and dependencies, and output layer which produces the final prediction. Backpropagation. This is a core algorithm for training neural networks. It uses gradient descent to adjust the weights of the network based on the error between the predicted and actual outputs. The error is propagated back through the network, allowing the weights to be updated in a way that minimizes the overall error. Universal approximation theorem. which is a theoretical result that states that a feed-forward neural network with a single hidden layer containing a finite number of neurons can approximate any continuous function on a compact subset of R to the power n. This means that in principle, neural networks can model arbitrarily complex relationships in data. Applications of this are image classification, handwritten digit recognition, spam filtering, and financial forecasting. Convolutional neural networks, CNNs. This is a specialized architecture designed for processing grid-like data, images, and videos. Key components include convolutional layers, which apply filters or kernels to the input data, extracting local features like edges, corners, and textures. And pooling layers that reduce the spatial dimensions of the data while retaining important features, making the network more computationally efficient and less prone to overfitting. Image recognition power. CNNs have revolutionized image recognition tasks, achieving human-level performance in many cases. They use in object detection, identifying and locating objects in images like cars, people. Image segmentation by dividing an image into meaningful regions. Facial recognition by identifying individuals from the facial features. Self-driving cars that process camera data or sensor data to recognize pedestrians, traffic signs, and other vehicles. Recurrent neural networks, RNNs, just sequential data designed to process. RNNs are designed to process sequential data where the order of the input matters, for example, time series, text, speech. RNNs have a hidden state that captures information from previous inputs, allowing them to model dependencies over time. Applications of this are natural language processing, speech recognition, and time series forecasting, predicting stock prices, weather patterns, etc. Challenges of this are vanishing and exploding gradients. The gradient signals used for training can become very small or very large as they propagate through time, hindering the learning process. RNNs can also struggle to capture long-term dependencies in sequences. Transformers and tension mechanism, where each element in a sequence attends to all other elements, allowing the model to weigh the importance of different parts of the input when making predictions. Unlike RNNs, transformers can process input sequences in parallel, making them much faster to train on large data sets. Transformers have achieved state-of-the-art results in many NLP tasks, including machine translation, text summarization, and question answering, also been successfully applied to other domains like image and video creation and processing and editing. Part 3. Applications, limitations, and the future of machine learning. Real-world applications. NLP, which is where we use machine learning to understand, interpret, and generate human language, is used in machine translation, sentiment analysis, determining the emotional tone of text. Chatbots, simulating human conversations for customer service, information retrieval, etc. Text summarization and text generation. Challenges are ambiguity, context, nuances of language, cultural differences. Computer vision, where we would allow computers to see and interpret visual data from the world. The applications of this are image recognition, object detection, facial recognition, and image generation, where we create realistic images from text descriptions or other inputs, for example, general adversarial networks. The challenges of this are variations in lighting, occlusion, viewpoint changes, the need for large annotated data sets. Recommendation systems, where we provide personalized suggestions for products, services, or content based on user preferences and behavior. So approaches for recommendation systems are collaborative filtering, where we recommend items based on similar user preferences. Content-based filtering, where it recommends items based on the attributes of items the users liked before. Hybrid methods, where we combine both approaches for improved performance. Applications of this are e-commerce, suggesting products to customers, social media, recommending friends, groups, contents, feeds, etc., posts, and news, personalizing news feeds for readers. The challenges of this are cold start problem, new users or items, the filter bubble, the limited exposure to diverse content, and privacy concerns. Healthcare. We apply ML to improve medical diagnosis, treatment, and patient care. For example, using it in areas like disease diagnosis, drug discovery. Finance. We use ML for things like fraud detection, algorithmic trading, credit scoring, and customer service. Let's not discuss some limitations of machine learning. While it has demonstrated remarkable capabilities, it's crucial to acknowledge its limitations to set realistic expectations and guide responsible development. Data dependency. ML models are only as good as the data they are trained on. If the data is biased, incomplete, or unrepresentative, the model's predictions and decisions will be flawed. Garbage in, garbage out. A common phrase used in computer science. This is also perfectly applicable to ML. Even the most sophisticated algorithms will produce meaningless results if fed with low quality garbage. Data collection and annotation. Acquiring large, high quality data sets can be expensive and time consuming, especially for specialized domains. Labeling data often requires human expertise. For example, a facial recognition system trained primarily on images of lighter skinned individuals may perform poorly on darker skinned individuals, leading to past outcomes. Interpretability and explainability, the black box problem. Many ML models, especially deep neural networks, are considered black boxes because their decision-making processes are opaque and difficult to interpret. Lack of transparency can be problematic in high-stakes domains like healthcare or finance, where understanding the reasoning behind a model's decision is crucial. Explainable AI or XAI is a growing field of research focused on developing techniques to make ML models more transparent and interpretable. Example, a loan approval model might deny a loan application without providing a clear explanation, leaving the applicant frustrated and unsure of how to improve the chances. Overfitting and underfitting. Briefly touched upon this, but there's a Goldilocks dilemma. Finding the right balance between model complexity and generalization is a constant challenge in ML. Techniques like regularization and cross-validation are used to mitigate overfitting and ensure models generalize well to new data. Bias and fairness. ML models can inadvertently perpetuate or even amplify biases present in the training data. Fairness of ML is a research focus based on developing algorithms and techniques to ensure fairness in ML systems. Bias mitigation strategies. These include careful data collection and pre-processing, algorithmic adjustments, and post-processing techniques to correct for biased predictions. An example of this is hiring algorithm trained on historical data might unfairly discriminate against certain demographic groups if the training data reflects past hiring biases. Computational costs. Training large and complex ML models, especially deep learning models, requires significant computational resources, powerful GPUs, and large amounts of memory and electricity. The environmental impact of this can be quite significant. Ongoing research focuses on developing more efficient algorithms and hardware architectures to reduce the computational cost of ML. The lack of general intelligence. Current ML models are specialized for narrow tasks, like image recognition, language translation, and lack the general intelligence, common sense reasoning of humans. Many applications, human expertise is still very essential. Let's talk about some future trends that we can predict based on where the world of ML is going. Explainable AI, XAI. It's building trust in AI systems, ensuring fairness and accountability, enabling humans to understand and control AI systems and decision making. Some techniques for this are local interpretable model agnostic explanations, or LIME, where we perturb input features and observe the model's predictions to generate explanations. sharply additive explanations, assigning important values to features based on the contributions to the model's outputs. Attention mechanisms, where we highlight the parts of the input that the model focuses on when making predictions. Challenges, balancing model performance with interpretability, developing explanations that are understandable to experts. Federated learning is where we train our models on decentralized data sources, for example, smartphones, IoT devices, without moving the data to a central server. This preserves data privacy while still allowing the model to learn from a large pool of data. Applications of this are healthcare and mobile devices. The challenges for this are communication efficiency, heterogeneity of data sources, AutoML, where we automate the end-to-end ML pipeline, including data pre-processing, feature engineering, model selection, hyperparameter tuning, and model deployment. This democratizes ML by enabling non-experts to build effective models. The benefits of this are it reduces the need for manual intervention, accelerates the model development process, improves model performance by exploring a wider range of options. The challenges for this are require substantial computational resources, the risk of over-reliance on automated systems without human oversight. AI ethics and regulation. It's important to address the potential negative impacts of AI, such as job displacement, biased decision making, and misuse of AI technologies. We need to develop ethical frameworks for AI, balancing innovation with regulation, ensuring global cooperation. With that, we end the lecture. As we conclude our exploration of machine learning, one thing is abundantly clear. This is not just a technological revolution, it is a paradigm shift in how we approach problem solving, decision making, and innovation. ML has the power to unlock new discoveries, drive economic growth, and address some of humanity's most pressing challenges. But with this power comes great responsibility. We must strive for ethical AI development, ensuring fairness, transparency, and accountability. We must be mindful of the potential biases lurking in our data and algorithms, and we must prepare for a future where humans and machines work together in unprecedented ways. The future of machine learning is not just about building smarter algorithms, it's about creating a better world. As you step away from this lecture, I encourage you to carry the knowledge you've gained, the questions you've pondered, and the inspiration you've found into your own endeavors. Together we can shape a future where machine learning services serves as a force for good, empowering us to achieve more than we ever thought possible. Thanks for your time.